This video is the second half of Module 11 for physics on waves. And we're going to start by watching a video of a double slit experiment that examines whether light is a wave or not. So let's take a look at this video.
What is light?
What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras.
We all have auras.
Which are light?
Yes, they are.
It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes in your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right?
Yeah.
It would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today. Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight. I was thinking about doing it in a box, like a fridge box.
And you could take it out on the street.
Taking it out on the street. Could I possibly interview you guys for about a minute? We're doing a science experiment. What I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm gonna place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom
Well,
of
the
the
obvious
box?
thing you think you're going to see is you're going to see two lines.
Two lines on the bottom of the box. Two bright bands.
Two little lines.
Yeah.
I think it'll be one line instead of two.
I could expect to see the whole box lit up.
It'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colours.
There, have a look. You expected to see kind of one line. Is that what you see?
No.
I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, two either side.
The two on the outside are multicolored, and the one in the middle is just white.
And kind of a rainbow.
The rainbow of colour as well.
Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots now. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
Two slits.
two slits. That's incredible.
But all we're doing is we're putting a light through two very narrow slits side by side. So how does this make any sense?
There's some kind of principle involved there that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that?
Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see two bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light cancelling itself out.
This is basically the same as like having two drops of water fall in a swimming pool.
That's right.
Exactly the same
And then they go
pattern.
and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, and then a dark spot, and then a bright spot. Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. So you saw the ones to the right were slightly colored.
Yeah, it's
that's
starting to
because
go burgundy.
the reds are going to meet up at different places than the blues.
And that's all that makes the colour differences, is different wavelengths.
Exactly.
That's amazing.
So the difference
So,
between
there's
red
so
and
that,
blue,
that red bin over there and the green part is just, I'm seeing
It's a
that, and
different-
it's just different
different
wavelengths. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, mate.
Hey, thank you.
I have been enlightened, literally.
That the scientific community can
So Young's double slit experiment is the classic experiment that is used to show that light is a wave. So if light is a wave, we said that a wave, in order for something to be a wave, it has to propagate through a medium. So then the question then became, what is the medium through which light oscillates and propagates? And there was another physicist whose last name is Maxwell, James Clerk Maxwell, in 1873. And he did a series of, he came up with a series of equations that looked at the relationship between electrical and magnetic phenomena. And he was able to show that electrical waves and magnetic waves are related, or electrical fields and magnetic fields are related to each other, and that you can predict the speed of that relationship as being the speed of light. So through Maxwell's the development of his equations, he was able to show that that light is really an electromagnetic wave. If you look in your book, on figure 11.8, you will see a drawing that basically is the generally accepted view of a light wave, and that is that the magnetic fields and the electrical fields are perpendicular to each other. And so the idea then is that light is an electromagnetic wave. Now, so therefore, if that is true, then we can use the equation that we've been using for sound waves. We can use the same equation then for light waves, so that we have the same relationship between frequency and wavelength. And now in this case, the velocity is going to be equal to the speed of light, which is 3.0 times 10 to the 8 meters per second. Okay, so when we look at wavelengths, the wavelengths can be very small, they can be very large, and there's only, if you look at figure 11.9 in your book, there's the frequency of light. There's a very small visible spectrum. So that very small portion that is visible light, and you probably have learned the visible light as Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. So these represent the different wavelengths for the visible light spectrum, but there are wavelengths on both sides of this, shorter and longer, so that X-rays that we use in have medical applications, or gamma rays that are used for also for some medical applications, they have shorter wavelengths, and then longer wavelengths are things like microwaves, FM radio, AM radio, etc. And then the visible wavelength, the visible light would be in between those. The units for wavelength in the visible spectrum are nanometers. And a nanometer is 10 to the negative 9 meters. So red light has a wavelength of 700 nanometers. So that would be 700 times 10 to the negative 9 meters. And then on the other side, violet light, or the violet light has a wavelength of 400 nanometers. And so that would be 400 times 10 to the negative 9 meters. So nanometers, 10 to the negative 9. Okay, before we go any farther, let's first look at the relationship between light and sound. So light travels much faster than sound. And we said that the speed of light is equal to 3.0 times 10 to the 8 meters per second. So one phenomenon that you have probably experienced, because light travels so much faster than sound, is when you see lightning, but then you hear thunder sometime after that. And that the difference there is because we assume that because light travels so rapidly, we assume that we see the light at the instant that it takes place, but then the sound takes a while for it to reach our ears. So you can actually determine how far away lightning is if you know how long if you know the time period between seeing the lightning flash and hearing the thunder. So in example 11.3 in your book, we are given that a physicist sees a flash of lightning and then hears a thunderclap 1 second later, and the temperature is 15 degrees C. Okay, so there's 1.00 seconds between the lightning, seeing the lightning and hearing the thunder. Okay, we want to know how far away was the lightning. Okay, so we know that distance is equal to velocity times time, right? And we were given the time as 1 second. So if we can determine the velocity at this temperature, then we should be able to, if we can determine the velocity of the sound, then we should be able to determine how far away the lightning was. So we can use our equation for the velocity of sound. We know that velocity is equal to 331.5 plus or minus, I'm sorry, just plus, sorry, I'm confusing this with something else, plus 0.606 times the temperature, and we don't include any units there, and our in the temperature, and then our final units are meters per second. So if we do this math and with our significant figures, we would get a velocity of 340.6 meters per second. Okay, so now we know that distance is equal to velocity. So we have the velocity as 340.6 meters per second times 1 second. So we can have three significant figures. So the distance then is 341 meters. So the lightning that took 1 second for us to hear the thunder associated with it, the lightning was 341 meters away. Okay, let's go ahead and do UNWRON 11.5. So if you hear a thunderclap 2.5 seconds after you hear the thunder, or after you see the lightning, how far away was the lightning if the temperature is 20.0 degrees C? Okay, so again, we know that distance is equal to velocity times time. We're given the time, and so we can determine the velocity. Velocity is 331.5 plus 0.606 times 20 degrees C. So the velocity then, with three significant figures or three significant figures comes out to 300 and, well, actually we can go out to the 10th place, so it's 343.6 meters per second as the velocity. So then distance is equal to the velocity, 343.6 meters per second times the time. It took 2.5 seconds to get there, so we're going to be limited to two significant figures. So this comes out to 859 meters, because seconds are going to cancel. So with two significant figures, it would be 860 meters. So the lightning, if it takes 2.5 seconds to hear the thunder, the lightning was 860 meters away. Okay, and then we'll go ahead and do on your own 11.6. And this one says that we have the starter's gun goes off at a race, and you see the smoke from the gun. When will you hear the sound if the starter is 402 meters away and the temperature is 25 degrees C? Okay, so again, we're going to use our equation of distance equals velocity times time. So now we're going to solve for time. So it's going to be the distance divided by velocity. It's going to give us time. So let's first figure out the velocity. So the velocity of sound is going to be 331.5 plus 0.606 times 25, and that's going to be, the whole thing will be in meters per second. So the velocity comes out to 346.7 meters per second. So then that and we're given the distance as 402 meters. So 402 meters divided by 346.7 meters per second. So meters are going to cancel. You'll be left with units for seconds. And looks like we can have three significant figures. So the answer would be 1.16 seconds. So 1.16 seconds will elapse between the time when the starter gun, when you see the smoke from the starter gun, and when you hear the starter gun. Okay, so let's get back then to the idea that light is a wave, and that is a generally accepted idea. Let's go ahead and do a couple of problems related to that. First, we'll do on your own 11.7. And 11.7 says that a recently developed laser used in the treatment of skin disorders produces a light produces light with a wavelength of 578 nanometers. And then we are asked, what, according to figure 11.10, what color is this light? So if you look on page 371, you see that between 550 and 600 nanometers, the light is yellow. Okay, and then we are asked, what is its frequency? Okay, so we know that frequency is velocity divided by wavelength. Velocity for the speed of light is 3.0 times 10 to the 8 meters per second. And wavelength we were given as 578 nanometers, which is 578 times 10 to the 9th meters. So the meters are going to cancel, and we'll be left with 1 over second, which is a hertz. So the frequency then equals 5.2 times 10 to the 14 hertz. Okay, so that is on your own 11.7. Okay, now let's look at on your own 11.8. Okay, and this one, this says that the waves used to send radio signals are electromagnetic waves. I often listen to a radio station that transmits waves with a frequency of 1,240 kilohertz. What is the wavelength of those waves? Okay, so first of all, we need to get these, since everything else we're dealing with is in hertz, we need to get that into hertz. So we just multiplied by 1,000, so we're just going to add 3 zeros to this. Okay, so it would be that many hertz. And then we just need to figure out the wavelength. So frequency is equal to velocity divided by wavelength. So we'll multiply both sides by wavelength. That gets rid of them there. Divide both sides by frequency. That gets rid of that there. So then wavelength is equal to velocity divided by frequency. Okay, so let's go ahead and erase this. Okay, so the velocity for the speed of light is 3.0 times 10 to the 8 meters per second. And frequency we said was 1,240,000 hertz, which is 1 per second. Okay, so the seconds are going to cancel, and you're going to be left with meters. So if we do that math, and we can have two significant figures, you should get 2.4 times 10 squared meters. This may have come out as 0.0024 times 10 to the 5th meters. So then if we move it three spaces, then that would make that 2.4 times 10 squared meters. And you could have also said 240 meters and still been okay on your significant figures. Okay, so that's application of light waves, application of our the formula that shows the relationship between wavelength and frequency applied to light waves. Okay, now we have said, and Young's double slit experiment supports the idea that light is a wave. So when you shine a light on a metal surface, the electrons will fly off of that metal, and those electrons are called photoelectrons because they're associated with light. And if light is a wave, that makes sense. Because waves have energy, so it makes sense that the electrons would absorb energy, and when they absorb enough energy, then they can break free. So the fact that light, that when you shine a light on a metal, that they break free, that can be consistent with the idea that light is a wave. However, there have been some other observations that don't make sense if light is a wave. And your book talks about your book enumerates all of these. The first one is that the electrons are ejected off of the metal when you shine a light onto the metal, they are ejected off of the metal within a few billionths of a second. So very, very fast. And if light is a wave, the electrons should have to soak up energy, and that takes time. So it doesn't really, the fact that they are ejected so quickly doesn't really fit with the idea of light being a wave. And also, the lower the intensity of light, the more time it should take, and yet it's been shown that it doesn't matter how intense the light is, the electrons are still emitted right after the light hits the metal. So this isn't consistent with light being a wave. Okay, so, and then the other one is what I just said, that the intensity of the light has no effect on the energy of the electrons. So if light is a wave, the energy that light gives the electrons should be proportional to the intensity of the light, because remember, amplitude in a light wave, the amplitude is an expression of the amount of energy that is given, and yet that isn't what is seen. It doesn't matter what the intensity of the light is. The intensity of light doesn't affect the way that those electrons come off of the metal. Another observation was that each metal had its own cutoff frequency. So the cutoff frequency of when the electrons would come off the metal was different depending on what the metal was. So if light was below that frequency, then the electrons wouldn't be emitted. And then lastly, the amount of energy that the electrons had when they were emitted from the metal was directly related to the frequency of the light and not to the intensity of the light. So these last two things seem to indicate that the frequency of light has something to do with its energy. So if that is the case, then these observations are not consistent with light being a wave. And yet we still have a lot of evidence that light is a wave. So Einstein he came up with the idea, and he assumed that light is a stream of particles. And he thought that these particles come in little bundles. So he agreed that they're electromagnetic, and that they come in these bundles that he called photons. And he said that the energy of the light, which is signified with the letter E, is directly proportional to the frequency. So we have this equation then. The energy of the light is proportional to the frequency, and this letter H stands for a standard constant, which is called Planck's constant. So Einstein said that if light is composed of individual photons, then photons and electrons in the metal will collide with each other, and the energy goes to the electrons, and they break away from the metal. And they should break free as soon as the light was turned on. So the intensity of the light would just mean that there were more photons, not that there was more energy. So the energy of the photons depends on the frequency of the light. So if you're below a certain frequency for a particular metal, then the electrons wouldn't come off. And that the amount of energy needed for the electrons to come off of the metal would vary with different metals, because different metals hold on to their electrons with different strengths. So Einstein explained that the energy is directly related to the frequency, and the unit that we use for the energy is called an electron volt, and 1.000 electron volts is equal to 1.602 times 10 to the negative 19 joules. So you can see that this is a very, if you think about a joule, this is a very small amount of energy. And Planck's constant that we saw before, H, is equal to 4.14 times 10 to the negative 15 electron volts times seconds. Okay, so you'll always be given that value. That's not a value that you will need to that's not a value that you will need to memorize. You will be given that value. So so what do we say then about light? Well, because there is evidence that light is a wave, and that light is also a particle, then we talk about the wave-particle duality of light. because there is evidence to suggest that light acts as both a wave and a particle. So when light, again, if we have a piece of metal and light comes in and hits that metal, it's going to come in with some energy. And if there is enough energy in the light, then it will free some electrons from that metal. And the thing that seems to determine that is that there is a cutoff frequency there's a cutoff frequency for each metal to free those electrons. So it doesn't matter how bright the light is, it depends on the frequency. So let's say, like if you had a ball down inside a hole, so this is like an electron down here, and if you hit the ball with enough energy, well, that ball is going to come out of the hole. But if you don't hit it with enough energy, it's going to remain in the hole. And so the energy that you hit it with is based on the frequency. So some colors emit electrons and others don't, depending on their frequency. So it doesn't matter the amplitude of the light, it matters the frequency of the light. So for example, ultraviolet light will emit electrons, but red light will not. Okay, so ultraviolet light will, red light will not. So it doesn't matter how much red light you fire, how much red light you shine on a metal, it does not have the energy, it doesn't have the frequency to emit electrons. So no matter how much red light, no matter the intensity of the red light, you're not going to get electrons emitted. Okay, so how does this all apply in terms of physics? So let's look at example 11.4. And so example 11.4 tells us that sodium metal has a work function. Actually, let me go back up and define this term work function. So work function is defined as the amount of energy that it takes for electrons to escape the metal. How much energy does it take for electrons to escape the metal? Remember, we said that's going to vary depending on the metal, because different metals hold on to their electrons with different amounts of strength. Okay, so that's the work function, and we abbreviate that as E. Okay, so the question then, the problem then says, so sodium metal has a work function of 2.28 electron volts. Okay, so that's how much energy it takes for the electrons to escape from the metal. If blue light with a wavelength of 4.25 times 10 to the negative 7 meters is shined on sodium, what is the kinetic energy of the electrons that are emitted from the metal? Okay, so remember that So this number tells us how much energy it takes for electrons to escape from the metal. So if an electron has this much energy, it will be able to break free, but it'll take this much energy for it to do that. So if this wavelength of light has more energy than that, then the difference will be in kinetic energy. So remember that the thing that determines the work function or the energy is the frequency. So let's go ahead and figure out what is the frequency of this wavelength. So 3.0 times 10 to the 8 meters per second divided by 4.25 times 10 to the negative 7 meters. So the meters are going to cancel. So the frequency for this light is 7.1 times 10 to the 14, 1 per second. 7.10, oh no, just 7.1 times 10 to the 14, 1 per second. Okay, or hertz. Okay, so now we can go ahead and figure out the energy for this frequency of light. Okay, so we know that energy is equal to Planck's constant times the frequency. So the frequency of that wavelength of light that we were given is 7.1. So here we're going to put 7.1 times 10 to the 14, 1 over seconds. And then you will be given Planck's constant, and Planck's constant is 4.14. Let's just write this all in here. Okay, so Planck's constant is 4.14 times 10 to the negative 15 electron volts times seconds. And then the frequency we said was 7.1 times 10 to the 14, 1 per second. Okay, so the seconds are going to cancel, and you will be left that E is equal to 2.9 electron volts. Okay, so that wavelength, the blue light has an energy of this amount, and when we shine it onto metal, onto the sodium metal, it takes this much energy to free the electron. So then what is the difference between them? 2.9 minus 2.28 electron volts. And we can go out to the tenths place here since we're subtracting. So the answer would be 0.6 electron volts. So the maximum potential electron energy then would be 0.6 electron volts. Takes this much for them to break free. It had this much, and so the energy that those electrons would possess, the maximum amount that they could possess, would be 0.6 electron volts, because not every collision of those electrons is going to result in all of the energy being transferred to an electron. So this would be the maximum amount. Some of them would be less. Okay, let's do on your own 11.9, 11.10, and then we'll be done with this one. So on your own 11.9. Cesium has a work function of 2.14 electron volts. And we're going to shine a green light that has a wavelength of 501 nanometers. What is the maximum kinetic energy that the electrons will have when they leave the metal? Okay, so we know that frequency is equal to the velocity divided by the wavelength. And remember, frequency is what we know that energy is equal to Planck's constant times frequency. So we first have to determine the frequency. So it's going to be 3.0 times 10 to the 8 meters per second. And then we'll divide that by the wavelength, which is 501 times 10 to the negative 9 meters. So meters are going to cancel. You'll be left with 1 over meters, or 1 over seconds, which is a hertz. So for this, you should get 5.9 times 10 to the 14 hertz. Okay, so and then we can plug that frequency into our equation here. You'll be given H. H is 4.14 times 10 to the negative 15 electron volts. And the frequency is 5.9 times 10 to the 14 1 per second. This is electron volts times seconds. This is times seconds. Let's go ahead and put that in there. Electron volts times seconds. And then we'll multiply that times 5.9 times 10 to the 14, 1 per second. So the seconds are going to cancel, and E will be equal to 2.5 electron volts. Okay, so it takes this much energy for the electrons with green light shining on cesium, and we have this much. So we take the difference between those two to give us the maximum kinetic energy that the electrons could have as they come off of that cesium metal. So 2.5 electron volts minus 2.14 electron volts. So we can go out to the 10th place, and you should get 0.36 electron volts, but we can only go out to 10th place since we're subtracting here. So it would be 0.4 electron volts. So so the energy of the photon shining on the metal, if all of it is given to an electron, then the electron will have this much, this many electron volts, and it's going to take this much to break free. So when it breaks free, it would have that. It would have a maximum amount of that much kinetic energy. Okay, one more we'll do on around 11.10. Okay, in this question we are told that a metal emits electrons when illuminated with light. However, if the wavelength is greater than 195 nanometers, no electrons are emitted. So 195 nanometers, and so that's the wavelength of the light, and we want to know what is the work function of the metal. Okay, so so remember again, work function is the energy that the metal, it's the energy that the metal holds on to those electrons. So if it gets more than that, then the electrons will escape from the metal. So if what this question is telling us is that if the wavelength is 195 or less, then no electrons will be emitted. But if it has greater than 195, then no electrons would be emitted. So frequency is equal to velocity divided by wavelength. So we're going to have 3.0 times 10 to the 8 meters per second. And the wavelength was 195 times 10 to the negative 9th meters. Meters will cancel, so that the frequency will be equal to 1.5 times 10 to the 15 1 per seconds, or hertz. Okay, so now with that frequency, now we can look at E. We can look at the work function. So E is equal to H times F, and H is 4.14 times 10 to the negative 15 electron volts times seconds, and then we'll multiply that times this number for frequency. Let's scoot everything over here. And then multiply that times the frequency, 1.5 times 10 to the 15 1 per seconds. So the seconds are going to cancel, and we will get that E is equal to 6.2 with two significant figures, 6.2 electron volts. So the energy of this would be the amount of energy that the photons have when they hit the metal. So that's the work function of that metal that we were given. We're not told what the metal is, but we're given its frequency, and therefore we can determine its work function. Okay, so that pretty much wraps up Module 11, in which we looked at both sound waves and light waves.